Welcome to Electronic Devices and Circuits Lab. So in this video, today we are going to learn about the clamper circuit. So the other name of this clamper circuit is DC restorer. So first of all, we need to understand what this clamper circuit does. Okay. So if you see this definition, so the clamping network is one that will clamp a signal to a different DC level. So now we have to understand what is this meaning. Like if we are saying that it is clamping a signal to a particular different DC level, what does it mean? That we have to understand. So this clamping means you can understand in the other words like it is a shifting of a signal either in the upward direction or in the downward direction based on the network. So first you try to understand what does it mean by having a different DC level. Okay, then we will be seeing that how it is upward shifting or downward shifting. Okay, so that we have to understand first. So let us suppose this particular signal. Okay, we have this particular square wave, and this square wave is having its excursion in between minus V volt to plus V volt. Okay, so its peak to peak variation is of 2V volt. Okay, so here you can see this waveform. This waveform is actually symmetrical about this 0 volt axis. Okay, this is our 0 volt axis. And here you can see this waveform is actually symmetrically arranged about this particular 0 volt axis. And if you calculate the average value of this particular waveform in a particular period of this particular waveform. So for example, here you can see that the time period of this particular signal is T, capital T here you can see. So if you calculate the average value of this particular DC signal, then you will find that this upper half portion is having its positive value and here it is having a negative value. So altogether you will find that these areas will be cancelled each other and you will find that this average value of this particular waveform over a particular time period is equals to 0. And therefore, this value is having its corresponding DC level equals to 0. And that is also, it is actually visible from the graph itself. You can see that this particular waveform is actually symmetrically arranged around the 0 volt axis. Okay. Similarly, you can also consider a sinusoidal wave. Okay, so here you can see that if suppose we are having a sinusoidal wave, so first you consider this blue line, okay, this blue sinusoidal curve. So let us suppose we are having a sinusoidal, pure sinusoidal curve without any DC component. In that time, you will find that this particular sinusoidal curve is making a symmetrical excursion between this, means around this 0 volt axis. So this is our you can say this is our ground level, or you can say that it is a 0 volt level. Okay, so here this potential or this value of or the magnitude of the sinusoidal wave will be 0. So this is our 0 axis. Okay, 0 volt axis, and here you can find that this sinusoidal wave is actually arranged symmetrically about this particular 0 volt axis. So suppose if you add any DC value, okay, if you add any positive DC value to this particular waveform, then obviously this waveform will be get upshifted. So whatever be the values, it is going to be added with a certain positive voltage. Okay, so if I add, let us suppose 3 volt of DC. Okay, so here you can see because this blue curve is actually making excursion in between -5 to +5. Okay, its minimum value is -5 volt and its maximum value is +5 volt. So if you add this +3 volt to this particular waveform, the entire waveform will be shifted upward by 3 volt. Okay, so here you can see this is this was earlier at 5 volts. So now this green signal, you can see this green waveform. So now this signal has been shifted. Okay, and this magnitude will become 8 volt. Okay, and then this waveform will start at 3 volt. Okay, because we have added 3 volt of DC signal. Okay, so this was earlier started at 0 volt. So now this will be starting at the 3 volt. So here you can see that if you draw a line, okay, draw a DC line, okay, a constant line parallel to this axis, this will be your level corresponding to 3 volt. So you can see that this particular waveform is actually making an excursion around this 3 volt curve. So now I can say that this green signal is actually clamped to a particular 3-volt DC level. Okay. So this is the meaning of clamping a signal to a different DC level. So if you add a negative voltage, okay, if you add a negative DC voltage, that time this blue curve will be downshifted. Okay, it will be getting downshifted. So that is the meaning of clamping a signal to a different DC level that you have to first understand. So now, if you wish to perform such operation, okay, if you want to shift a particular signal to a particular DC level, that time we need to have a particular circuit, which is consist of a diode, okay, in parallel with resistors and a capacitor connected in this series arm. So as you know that this is called as the series arm and this is our shunt arm. So normally in the clamper circuit, this diode is always being connected in the this particular shunt arm along with a resistance which will be connected in parallel to the diode. Okay. So if you try to analyze this circuit, okay, first we need to analyze this circuit, how this circuit is actually going to shift the input waveform, that we have to first analyze. So let us suppose that this diode is ideal. Okay. So normally we are having practical diodes, and in the case of practical diodes, there will be a certain finite cut-in voltage that we need to take care, and after that only the diode will generally get turned on. Okay. But here, if you consider it to be an ideal diode, in that case, you know that whenever there is a any voltage which is greater than 0 volt, if we apply at that time, this diode will get turned on, okay, because of the forward bias. Okay. So here you can see that when this positive half cycle of the square wave is going to appear, at that time this diode will become forward bias and it will be replaced by its equivalent short circuit. Okay, so that you can see here in the positive half cycle. Okay, so in that case it will be get short circuited. Okay, and then this capacitor will start charging through this particular cycle. Okay, so in this particular cycle, the current which is going to be flow, so almost all the currents will be passing through this particular diode only. This resistance will not take any current. The reason is that because it is having a very low resistance path, so you must be aware that the current is always following the low resistance path, because we are considering this to be an ideal diode. Okay, and therefore it will be having a resistance equals to 0, and therefore all the currents will be passing through this short circuit, and therefore this capacitor is going to be charged through this particular loop. Okay, means the current is flowing through this loop only, and therefore this capacitor is going to be charged. So you must be knowing that the capacitor will be charging with a certain charging time constant. Okay, so because this resistance offered by the diode, in the case of ideal diode, it will be very small or it is negligibly small. Okay, I can say that this capacitor is going to be charged instantly. Okay, so within no time this capacitor is going to be charged. So the meaning is that this voltage, because it was like here you can see we have applied plus V volt. Okay, so this capacitor will be fully charged up to plus V volt, and this will be the polarity. Okay, because current is passing in this direction, in the clockwise direction, this will become positive and this will become negative, and it will get fully charged. Similarly, when you consider this negative half cycle, because earlier in the positive half cycle this capacitor was charged, now this diode will be open circuited, it will become reverse bias when this negative half of the cycle will come. Okay, so this will be reverse biased and it will be becoming open circuit. So this has to be replaced by the open circuit, and that time we need to calculate what will be this open circuit voltage. Okay, so if you see this polarity, initially we had this plus V volt, so therefore this was equivalently to having this particular voltage minus and plus polarity. This was the polarity. Now, because we are taking minus V volt, so this polarity has been changed. Okay, it is becoming minus here, and this is plus. Okay, so now you can write the KVL expression into this particular loop. So you will find that this potential is minus V, then again it is plus to minus. So it will be again minus V. Okay, and then because it is charged up to minus volt, okay, and therefore it is minus V naught here, and then equals to 0, okay. So that particular voltage, V output voltage, if you find, it will be something equals to minus 2 V, okay. So that you can easily find out from this particular loop, okay. So you just write the KVL expression into this loop, and then you will be able to find what will be the open circuit voltage around the diode, okay, when we are having this negative half cycle of the input waveform. So we have already calculated what will be the voltage across this particular diode, because we are actually calculating the diode across this two terminal, okay. So because this resistance and this diode are in parallel, okay, so whatever be the potential across the diode, the same potential is going to appear across the resistance also, because both are in parallel. So here you can see, because it was short circuited when it is having the positive half cycle at the input side, so therefore the output voltage is going to be 0, okay, in the positive half cycle. So here you can see we are having this positive half cycle, okay. So when we have this positive half cycle up to time t/2, the output voltage was 0, okay. Here you can observe that this output voltage was 0. As soon as this negative half cycle will arrive, then that time we have already calculated this output voltage across this particular diode is equals to minus 2V. Okay, so here we have plotted this waveform. You can see it is minus 2V. Fine. And this way we are going to get this waveform. So now you try to observe these two different waveforms. So what we have said is, this clamper circuit, what is the function of the clamping network is to clamp a signal to a different DC level. So here you can see that this input waveform is having its peak to peak value is from minus V to V. It means that the peak to peak value of this particular signal was 2V, and its DC level was equals to 0 volt initially, okay. But after passing through this particular clamping network, here you can see that we have actually shifted down this signal. Okay, this input signal was actually shifted down, and we are going to get this type of waveform where you can find out this peak to peak value is remains constant. Okay, this is one of the very important property of the clamper circuit, is that the peak to peak variation of the output waveform will not change. So whatever be the peak to peak variation of the input waveform, the same variation is going to be appear across the output also. Okay, that peak to peak variation will remain same. It is equals to 2 volt. Okay, but what is the difference is that now if you calculate the average value of this particular waveform, so that average value will be equals to minus V volt. Here you can see that this average, if you calculate, you will find that this average equals to minus V volt. Okay. So now this particular signal, okay, this particular signal is now get clamped to this particular minus V volt DC level. Okay. So minus V volt DC level. So this way we are actually shifting the signals. Either it is in the upward direction or it is in the downward direction. We have to always care that while solving the clamper circuits, okay, these clamper circuits can have any kind of waveform, but normally we have to start solving this network for that particular cycle of the input waveform that will make the diode forward bias. Okay, you remember that. That will help you to find out the exact waveform. Otherwise, if you start with the negative cycle initially, then that time it may be going to give you a certain wrong results. It will give you a certain wrong mental picture. Okay, so you always try to start with that particular cycle of the input waveform that is going to make this diode forward bias, and that will allow the capacitor to charge. Okay, so once this capacitor will charge, then after you have to solve it for the other half cycle at which this diode will be turned off. Okay, and then you can get the exact output waveform. Okay, so here you can find that we are having a different kind of clamper circuits. Okay, so we can have this clamper circuit that we have already seen. We can also connect a certain DC supply, okay, in the clamping circuit network. Okay, suppose if we add a certain clamping a certain DC voltage. Okay, so here we can see that we have added a DC supply of V1 with this particular polarity. Okay, so if we add this particular polarity, if you remember in this case, when this positive cycle was coming, okay, that time this voltage, output voltage, was equals to 0 because this was equals to short circuit. Okay, it will be replaced by the short circuit. But here you can see that when we are adding this particular V1 voltage, when it will be get short circuited, the voltage across this two terminal that going to be appeared is equals to V1 volt. Okay, it will be positive V1. So here you can see that it is actually coming as a V1. And then in the negative half cycle, so one more thing that you can calculate is what will be the maximum voltage up to which this capacitor is going to be charged. Okay, so here you can see it is V1. So here if we applied voltage is VI. Okay, so that time if as we have seen it is equals to capital V here. Okay, so what will be the when capacitor will be going to be charged, the maximum voltage will be equals to capital V minus V1. Okay, that will be the voltage by which your capacitor will get charged. So therefore, when this negative half cycle will come, again you have to solve the KVL expression. Okay, and then you will be able to calculate this particular voltage. What will be this particular voltage? That you will be able to calculate by calculating the means writing the KVL expression into this particular loop. So hopefully you must be able to understand all these graphs. Okay, you have just we have changed the polarity over here. You can see that initially we were getting V1 over here, and then this peak to peak value will remain same equals to 2V, and you can also calculate what will be the DC level. Okay, you can calculate what will be the average value of this particular clamping network. Similarly, this will be the waveform if you change the polarity of the battery. Okay, even we can change the direction of your diode. Okay, so once you will change the direction of the diode, here we have downshifted the waveform. Okay, but here this waveform will be upshifted. Okay, based on this particular direction of the diode. Okay, similarly, again you can add certain DC component, power supply. Okay, DC power supply. Okay, and then you can change the polarity. You will be able to get this particular waveforms. So as I have said that in this particular example, I have just taken this square wave, okay, as the input, but we can also take the any waveform. Okay, so if we take the sinusoidal wave, we can have a different circuits. Okay, again the same circuits we are having, but we can also take the sinusoidal input waveform. So this will be our positive clamping circuits. Okay, so when the positive half cycle will come, okay, so that time you can you understand in this particular case we cannot start with the positive half cycle. You just to start negative half cycle, because at that time this diode will be turned on. Okay, that time you have to calculate what will be the what will be the voltage across this particular diode, and then you have to calculate accordingly what will be the value of the what will be the voltage across your capacitor. So if you start with this negative half cycle, you can find that when it is 0 volt, okay, initially when it is increasing, okay, then this voltage, okay, this voltage is means whenever it is a peak value, okay, here you can see that when we are having this negative half cycle, at that time you will start this particular writing the KVL expressions. Okay, so that time it will become forward bias, and as the voltage increases, okay, that time you will be finding that, because if it is a practical diode, okay, because here we are considering the practical diode, it is not a ideal diode. So when we are considering it to be a practical diode, and that time this will be offering a certain amount of resistance. Okay, and because of that you will find that there will be a certain increase in the voltage. Okay, it is not like a flat 0 volt. Okay, we will not be going to get a flat 0 volt, but a certain amount of voltage, where a voltage variation you are going to observe across this particular terminal. Okay, and after that you will find that it will get charged up to a maximum peak value of the input waveform. So here it is minus V. So here it will be polarity like plus and minus, and that way it is going to be charged, and then this will be having a particular voltage that you can calculate by writing the KVL expression. Similarly, we have a different kind of circuits. You can observe these circuits. Okay, so you can implement this circuit. So I'm just going to the MultiSim. Okay, and there you can just apply this input voltages, and then you can just observe this output waveforms. Okay, these are the different circuits that we can implement onto the MultiSim. I'm just going back to this particular software. Okay, so here you can see that I have just made this circuit. Okay, you can see one of the very important circuit, clamper circuit, that we have here. Okay, so one important observation about the clamper circuit is that in the clamper circuit, okay, there are 2-3 parameters that we have to take care in mind. Okay, first of all, because it is consist of capacitor and resistors. Okay, so we cannot choose this R and C value arbitrarily. Okay, so what we have to do is we have to keep in mind, because this capacitor should not discharge through this resistor. Okay, whenever this diode is in the off state, this capacitor should not discharge through this resistor. Okay, so this RC time constant, okay, discharging time constant of the capacitor should be very high as compared to the time period of your input waveform. Okay, if we are having a particular signal of a certain frequency, okay, that time we have to take care that these values, okay, that value should be, this RC time constant should be very much larger than the time period of your input signal. Okay, that we have to take care, otherwise you will be going to get the wrong output. That we have to take care. I will just show you. Okay, so first you try to understand, if you wish to just try to observe first this particular output. Okay, so here I am just making a simple circuit in which we have taken just 1 kilo ohm resistor, and then I'm applying a particular sinusoidal wave of 1 kilohertz. So peak value is equals to 1 volt, so its peak to peak value will be equals to 2 volt. Okay, so here you can see that if we apply this signal, and if you try to see this waveform, okay, you will see that we are having this red colored output, and another color is white color signal. Okay, this is our input and this is our output across this resistor. So here you can see that both input and output are actually the voltage across your 1 kilo ohm resistor. Okay, and therefore both the signals are actually overlapping, and we are not able to see both the signals. But if you wish, you can just make a certain offset. Okay, then you will be able to see this waveform. Okay, so just I'm making an offset. Okay, I'm just shifting down one of the signals. So I'm just shifting down this output signal. Here you can see that this is our red signal. Okay, this signal. Okay, and this is your white signal. Okay, which is you are connected to this particular point. So suppose if you wish, okay, if you wish to shift this signal, okay, means if you wish to shift the DC signal, right? Means here you can see that because this is your 0 volt line. Okay, this is our ground level. Okay, so this is our ground level in the circuit, and you can see that this AC signal is actually situated, or it is symmetrically arranged around this particular DC level. So this signal is actually having its average value equals to 0. So if you wish to change this DC level, okay, if you want to change that if you want to shift this particular AC signal, okay, its DC quantity, if you want to add, if you are adding this particular DC quantity into this particular signal, okay, we can add this. Okay, after adding it, you will find that this output waveform is actually going to be upshifted. Okay, and here you can see that it's average value. Okay, its average value is equals to 1 volt. Okay, here you can see that because this is your 0 volt, it is 1 volt, and this is your 2 volt. Okay, if you see 1 volt per division. Okay, so because it is 1 volt per division, and our ground level is this one, fine, this is our ground level. So here you can see that this is our waveform. Okay, and now its DC level is equals to 1 volt. Okay, so here you can see we can make a simple circuit in which we can shift the signal. Okay, keeping its peak to peak value equals to the input. Okay, we have not disturbed the peak to peak value, but we have changed the DC level of the input signal. But suppose if you don't want to do the same thing by adding a particular DC power supply, then how it can be done? Okay, the same thing can be done by the clamper circuit. So here we can see that we are having a clamper circuit. Okay, and I'm just taking this signal as 1 kilohertz. Okay, the frequency, and this input peak to peak value. This is V maximum. In fact, okay, so this is your V maximum value. So peak to peak value will be equal to 2 volt. So here we can see that if we apply this particular signal and then if you take this particular circuit, okay, so if you execute this circuit, okay, so you have to remember that constant, okay, that I said that this time constant, this discharging time constant for this capacitor, okay, it should be very, very large as compared to the time period of the input signal. Otherwise, you are not going to get the proper output because this capacitor will get discharged, okay? It will not charge up to its maximum value, but it is finding another path and it will be getting discharged. Fine. So if you execute this circuit, okay, you can observe this output. Okay, here is the output. So here you can see that we are having the input waveform. Okay, here you can see this white one is your input waveform. Okay, and we are actually you just make it 1 volt. Okay, 1 volt per division sensitivity. So now you can see that this is our input waveform, and we have taken the practical diode. Okay, in this case, you can see that this waveform is not coming exactly. Okay, it is not. It is a something some kind of deterioration in this particular waveform you may find. Okay, it is not properly coming as a pure sinusoidal wave. Okay, so what I can do is you can just either you can increase the resistance value, or even if you make it open circuit, it will work. Okay, so let me make it open circuit. So if you remove this connection, okay, now if you observe this output, because now this time constant becomes very large, okay, because R into C will become infinite because it is now replaced by an open circuit. Here you can see that this waveform will appear, okay, across the output. And now here you can easily see that this is our input waveform, and because it is having a negative clamper circuit, okay, so without any bias, it is a negative clamper circuit, so your signal is going to be downshifted, okay. And here you can see that it is in the positive half cycle, okay. The maximum voltage which is going to appear across the diode will be equals to the cut-in voltage, okay. So you may find that this voltage will be around 0.3 volt or 0.4 volt or 0.7 volt, depending on what kind of a diode it is, okay, whether it is germanium diode or a silicon diode, that much of voltage is going to be appeared across this particular diode. So that value you can see here, okay, that value you can see, okay, because it is a practical diode. If it is not a practical diode, then obviously when we are getting a peak value, still that value will be equals to something 0 volt, okay, it will be near about 0 volt. So this type of waveform we are going to get. Now you can see and you can calculate what will be this peak value, okay, even from the waveform only you can measure these values, right? You can measure these values, so you can bring out these pointers and then you can measure these values, okay, fine. So here you can see that what is this value and what is this is your pointer number 1. So here you can see that at T1 and this red one is connected to the channel B. So here you can see this reading. This value is at T1 is around 136.544 millivolt. Okay. And here you can find that this value is around minus 1.994 volt. Okay. That you can observe. This value minus 1.857 volt. Okay. So now you can calculate what is the peak to peak value. So peak to peak value, you can just calculate it as here showing like minus 1.99 volts. So it is almost equals to 2 volt. Okay. You just adjust this pointers, you will be getting this values exactly 2 volt. Okay. That you will be getting easily. So this way you can see this waveforms, you can observe this waveform. Okay. All the circuitry you can make, and then you will be able to get this results. Fine. So similarly, again, other way you can do is you can add a particular resistance or you can adjust this resistance and capacitance value such a way that you will be able to get the right waveform. Okay. See, normally in the practical circuits, we don't make it open circuit. If you make it open circuit, even if you disconnect this path, okay, if you are not having any input signal, this capacitor will not find any path to discharge. And therefore, normally what we do is we are actually keeping a certain values that will be sufficiently high. Okay, so during the connections, it should not discharge. But later on, whenever it is required, then we can make a short circuit and then we can. If you make it a little bit high, okay, if you make this values a little bit high, okay, both R and C, then you can calculate 10 microfarad multiplied with the 100 kilo ohms. If you calculate this RC value, you will be going to get this value equals to how much? This is 1000 milli, okay, milli seconds. So because here we are having this 1000 milliseconds, hopefully it is wrong or right. Okay, yes, it is 1000 milliseconds. 1000 milliseconds means it is around 1 second. Okay, so this is your 1 second time constant, and here we have applied the sinusoidal wave of 1 kilohertz frequency. So what will be the time period of the signal? That will be equals to 1 millisecond. So it is very much larger than that, and therefore this circuit should work properly. So here you can see this waveform. Okay, again we are getting the same output. Okay. So that we have to take care. You remember that we have to take care about this. You can change the waveform. You can choose any other waveform also. Okay, you can take the square wave. Okay, you can take the triangular wave and you can observe the output waveform. Again, you can try to connect a DC power supply and try to see what kind of changes in the output waveform can be observed. Just make it 1 volt, okay, and then try to see what kind of waveform we are going to observe. Okay, so first we need this, then only this changes will. Now you can just try to execute the circuit. Again, you will find that the signal is actually being shifted. Okay, we have added 1 volt of DC power supply, and here you can see that these two waveforms are actually getting upshifted again, and then we are getting this kind of waveform. So what you do, you just try to make a different value so that we will be able to properly observe the output. If you make it like 0.5 volt, okay, that time you will be able to see this waveform. Okay, so now if you see this waveform, okay, it is upshifted waveform, right? This waveform, the red one is the output waveform. So now you can see that it is upshifted again. If you change the polarity of this battery, okay, just you try to change the polarity of the battery. Here I'm just making a change in the polarity by putting this negative sign, okay, which is is multisim. But whenever you have the circuit, okay, whenever you have the circuit, okay, if you are implementing the circuit onto the breadboard, then you have to change the polarity. Okay, so if you change like this, then you can observe that this shifting of the signal is taking place at the downward side. So it is going to decided by this polarity, its values, okay, how the diode is being connected. Okay. This way, we are going to shift the signal either in the upward direction or in the downward direction. So this way, you can implement this circuit. So I hope that you must have understood how to implement a clamper circuit. Okay, so you try to implement all these circuits, whatever I have shown you, and you will be able to observe all these outputs. Okay, you always try to if you want to analyze the output waveform, you always start with that particular cycle of the input waveform that makes the diode forward biased, and then you try to solve for the that particular cycle in which it will become reverse bias and it will be replaced by a open circuit. Okay, and then you will be able to draw a mental picture what kind of waveform you are going to observe. So I hope you must have understood something about this particular clamper circuit. So try to implement all the circuit onto the multisim, and those who are performing the experiment onto the breadboard, they can also implement all these circuits, and hopefully they will be able to uh, observe this waveforms. Okay, all these waveforms you will be able to positive biased clamper, negative clamper, okay, negative biased clampers, all these outputs you will be able to observe. So if you have any further doubt, you let me know your doubts with your comments. Okay, if you find any difficulty, okay, circuit, or if you need any further explanation, please drop me a message in the And thank you for watching this video and stay connected with the channel for more updates.